formula for calculating DC resistance cannot be directly used for temperature adjustment of the effective Z values. The effective Z values are complex numbers that include both resistance and reactance components. The formula for DC resistance only adjusts for the change in resistance with temperature. AC resistance is the resistance offered by a conductor to the flow of alternating current. It is slightly higher than DC resistance due to the skin effect and proximity effect in conductors. AC reactance is the opposition to the flow of AC caused by either capacitance, which is inductive reactance, or inductance, which is capacitive reactance. It is measured in ohms. Inductive reactance occurs when current flows through a coil or inductor. Capacitive reactance occurs when current flows through a capacitor. AC impedance is the total opposition to the flow of AC. It is a complex number that includes both resistance and reactance. The formula for AC impedance is Z equals R plus JX, where R is the resistance in ohms, X is the reactance in ohms, and J is the imaginary unit, which is the square root of -1. Adjusting AC parameters for temperature changes requires specific methods and formulas depending on the parameter and the conductor material. For more information, consult IEEE Standard 835-2018, IEEE Recommended Practice for Calculating Short-Circuit Currents and Evaluating the Short-Circuit Capacity of Electrical Systems and Equipment, the National Electrical Code, and electrical engineering textbooks such as Fundamentals of Electric Circuits by Alexander and Sadiku. Let's delve deeper into AC resistance. AC resistance arises due to two primary phenomena. Firstly, the skin effect. Secondly, the proximity effect. The skin effect refers to the tendency of alternating current to flow primarily near the surface of a conductor, rather than uniformly throughout its cross-sectional area. This non-uniform current distribution effectively reduces the conductor's cross-sectional area, leading to an increase in resistance. The skin effect becomes more pronounced at higher frequencies as the current is increasingly confined to the surface. The depth to which the current penetrates, known as the skin depth, is inversely proportional to the square root of the frequency. The proximity effect, on the other hand, occurs when two or more conductors carrying alternating current are located close to each other. The magnetic field produced by one conductor induces eddy currents in the adjacent conductors. These eddy currents circulate within the conductors, opposing the main current flow and increasing the overall resistance. The proximity effect is also frequency dependent, becoming more significant at higher frequencies. Now let's examine AC reactance in greater detail. AC reactance is categorized into two types. Firstly, inductive reactance. Secondly, capacitive reactance. Inductive reactance arises from the presence of an inductor in an AC circuit. An inductor is a coil of wire that stores energy in a magnetic field when current flows through it. When an alternating current passes through an inductor, the changing current creates a changing magnetic field. This changing magnetic field, in turn, induces a back electromotive force or back volts in the inductor, which opposes the flow of current. The inductive reactance, denoted as X sub L, is directly proportional to the inductance, denoted as L, and the frequency, denoted as F, of the AC signal. The formula for inductive reactance is X sub L equals 2 pi FL. Capacitive reactance, conversely, arises from the presence of a capacitor in an AC circuit. A capacitor consists of two conductive plates separated by an insulating material called a dielectric. When an alternating current is applied to a capacitor, the capacitor charges and discharges repeatedly. The flow of current is impeded by the charging and discharging process, resulting in a capacitive reactance, denoted as X sub C. The capacitive reactance is inversely proportional to the capacitance, denoted as C, and the frequency, denoted as F, of the AC signal. The formula for capacitive reactance is X sub C equals 1 divided by 2 pi FC. Understanding AC impedance is crucial for analyzing AC circuits. AC impedance, denoted as C, is the total opposition to current flow in an AC circuit, encompassing both resistance and reactance. It is a complex quantity, represented as C equals R plus JX, where R is the resistance, X is the reactance, and J is the imaginary unit, the square root of -1. The magnitude of the impedance, denoted as the absolute value of C, is calculated as the square root of r squared plus x squared. The angle of the impedance, denoted as theta, is given by the arctangent of x divided by r. This angle represents the phase difference between the voltage and current in the AC circuit. In a purely resistive circuit, the impedance is equal to the resistance, and the phase angle is 0 degrees. In a purely inductive circuit, the impedance is equal to the inductive reactance, and the phase angle is 90 degrees. In a purely capacitive circuit, the impedance is equal to the capacitive reactance, and the phase angle is -90 degrees. When dealing with temperature adjustments of AC parameters, it's important to recognize that the temperature dependence of resistance and reactance can vary depending on the material and the specific parameter in question. For example, the resistance of a conductor typically increases with temperature, while the reactance of an inductor or capacitor may exhibit a more complex temperature dependence. To accurately adjust AC parameters for temperature changes, it's essential to consult relevant standards and engineering references that provide specific formulas and guidelines for the materials and parameters of interest. For conductors, the temperature coefficient of resistance is a key parameter. This coefficient quantifies the change in resistance per degree Celsius or Fahrenheit change in temperature. The formula for calculating the resistance at a different temperature is R sub T equals R sub 0 multiplied by 1 plus alpha multiplied by T minus T sub 0, where R sub T is the resistance at temperature T, R sub 0 is the resistance at the reference temperature T sub 0, and alpha is the temperature coefficient of resistance. For inductors and capacitors, the temperature dependence of reactance is influenced by factors such as the temperature coefficient of the dielectric material and the thermal expansion of the components. Manufacturers typically provide data sheets that specify the temperature characteristics of their components. When working with electrical systems and equipment, it's imperative to adhere to the guidelines and requirements outlined in relevant standards and codes, such as IEEE Standard 835-2018 and the National Electrical Code. These resources provide comprehensive information on calculating short-circuit currents, evaluating the short-circuit capacity of electrical systems, and ensuring the safe and reliable operation of electrical equipment. Let's consider some practical examples to illustrate the application of these concepts. Suppose we have a copper conductor with a resistance of 1 ohm at 20 degrees Celsius. The temperature coefficient of resistance for copper is approximately 0.393 per degree Celsius. If we want to determine the resistance of the conductor at 50 degrees Celsius, we can use the formula R sub T equals R sub 0 multiplied by 1 plus alpha multiplied by T minus T sub 0. Plugging in the values, we get R sub 50 equals 1 multiplied by 1 plus 0.393 multiplied by 50 minus 20, which equals approximately 1.118 ohms. Now let's consider an inductor with an inductance of 10 mH operating at a frequency of 60 Hz. The inductive reactance is calculated as X sub L equals 2 pi FL. Substituting the values, we get X sub L equals 2 multiplied by pi multiplied by 60 multiplied by 0.1, which equals approximately 3.77 ohms. Finally, let's consider a capacitor with a capacitance of 10 microfarads operating at a frequency of 60 Hz. The capacitive reactance is calculated as X sub C equals 1 divided by 2 pi Fc. Substituting the values, we get X sub C equals 1 divided by 2 multiplied by pi multiplied by 60 multiplied by 0.1, which equals approximately 265.26 ohms. In summary, understanding AC resistance, AC reactance, and AC impedance is essential for analyzing and designing AC circuits. Accurate temperature adjustment of AC parameters is crucial for ensuring the reliable and safe operation of electrical systems and equipment. By consulting relevant standards, codes, and engineering references, you can obtain the necessary information and guidance to perform these calculations effectively. The National Electrical Code provides comprehensive guidelines for electrical installations, including requirements for conductor sizing, overcurrent protection, and grounding. It is essential to adhere to the NEC requirements to ensure the safety of people and property. IEEE Standard 835-2018 offers detailed procedures for calculating short-circuit currents in electrical systems. These calculations are necessary for selecting appropriate protective devices, such as circuit breakers and fuses, to prevent damage to equipment and minimize the risk of electrical hazards. Electrical engineering textbooks, such as Fundamentals of Electric Circuits by Alexander and Sadako, provide a thorough treatment of AC circuit analysis and design. These textbooks cover topics such as sinusoidal waveforms, phasors, impedance, power, and resonance. By studying these topics, you can gain a deeper understanding of the behavior of AC circuits and systems. In addition to these resources, there are numerous online tools and calculators available that can assist you in performing AC circuit calculations. These tools can save you time and effort, and they can also help you to avoid errors. However, it is important to understand the underlying principles and assumptions behind these tools so that you can interpret the results correctly. When working with AC circuits, it is always important to exercise caution and follow proper safety procedures. AC voltages can be lethal, so it is essential to energize circuits before working on them. Always use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not qualified to work on AC circuits, consult a licensed electrician. Understanding the concepts of AC resistance, AC reactance, and AC impedance is crucial for anyone working with electrical systems. These concepts are fundamental to the design, analysis, and troubleshooting of AC circuits. By mastering these concepts, you can improve your understanding of electrical engineering and enhance your ability to solve electrical problems. Furthermore, consider that the accurate determination of impedance and its components, resistance and reactance, plays a vital role in power system studies, particularly in load flow and short-circuit analyses. Load flow studies are used to determine the voltage and current distribution throughout a power system under various operating conditions. These studies help engineers to optimize system performance, identify potential bottlenecks, and ensure that the system can meet the demands of its load. Short-circuit analyses, as mentioned earlier, are used to calculate the magnitude of fault currents that can occur in a power system. These calculations are essential for selecting appropriate protective devices and for ensuring that the system can withstand the stresses imposed by a fault. The impedance of transmission lines, transformers, generators, and other power system components directly affects the results of load flow and short-circuit studies. Therefore, it is crucial to have accurate impedance data for all components in the system. The temperature dependence of impedance can also have a significant impact on power system performance. For example, the resistance of transmission lines increases with temperature, which can lead to increased losses and reduced voltage stability. The reactance of transformers can also change with temperature, which can affect the reactive power balance in the system. Therefore, it is important to consider the temperature effects on impedance when performing power system studies. In addition to power system studies, the concepts of AC resistance, AC reactance, and AC impedance are also important in other areas of electrical engineering, such as electronics and communications. In electronics, impedance matching is a critical technique used to maximize the power transfer between different circuit components. In communications, impedance is used to characterize the behavior of transmission lines and antennas. A deep understanding of these concepts is essential for designing and analyzing electrical systems in a wide range of applications. Therefore, continuous learning and professional development are highly recommended for electrical engineers. Staying abreast of the latest advancements in electrical engineering, including new materials, technologies, and standards, is crucial for maintaining professional competence and for contributing to the development of innovative solutions. Participating in industry conferences, attending workshops, and reading technical journals are excellent ways to stay informed about the latest developments in the field. Engaging with the broader electrical engineering community through professional organizations such as the IEEE can also provide valuable opportunities for networking, collaboration, and knowledge sharing.